This example is going to be SAD wedge pair technique. Now, wedge pair is a maybe not so commonly now, but was a commonly used treatment beam arrangement for palliative cases, primarily maybe like a lateral head and neck, ipsilateral head and neck, or a posterior beam arrangement for spine vertebral bodies, if kidneys aren't in the way or if we're not blasting through a lung. Wedge pair can be at any angle less than 180 degrees apart, but typically they're roughly about 45 degrees apart. The wedge angle can be used to figure out what the hinge angle can be figured out from the hinge angle. The hinge angle is defined as the angle between the two beams. So in my case here, I have an RPO and an LPO field. The hinge angle would be 90 degrees in this case. The optimal wedge angle depends on beam energy, depth of treatment, as well as body contour. So while the hinge angle can get you close, really in the treatment planning system you're going to be going through a trial and error process. The reason that we do a wedged pair is because if you have beams that are less than 180 degrees apart, that aren't in a posterior, or that are not in a parallel opposed beam arrangement, essentially the hottest part from each of these beams contributes, and we end up with this hot spot at the intersection of the two beams closest to each other, and then it falls away and you get this unfavorable dose gradient falling from the surface of the patient. So we need to compensate for that dose gradient, and we're going to put wedges. Right now I have equally weighted beams. I have 15x. So if you are going on the beam data tables that are available on the website, make sure that you're following along on the proper data table. You're going to want 15 MV TMR. I have this calc point in here, spine calc point. I've named it a calc point, but that's where my isocenter for my fields are as well. I don't have any MLCs. If you look in 3 dimensions at my phantom, you can see how the beams are laid out in a posterior oblique nature. 225 and 135 are the gantry angles, so again a hinge angle of 90 degrees. I'm delivering 250 centigrade 15 fractions to 3750, normalized at the 100% isodose line at the spine calc point or isocenter. Now in order to get rid of this unfavorable dose gradient, I'm going to want to put wedges in. So I can go to the properties for my wedge, and I can put in, let's start off with a 45 left, and we'll do a 45 right, and I'll recalc the dose. Again, I have no heterogeneity correction, so it's a water equivalent phantom. The dose gradient in this case has improved. You can see my wedges. I have the heel of the wedges facing each other, since I had the hottest spot was in the beam intersection closest to each beam. So I want the heel of the wedge to face each other, the toe faces away. You've noticed that my dose gradient has decreased. I have a less 3D max dose. I also have almost no 110%. My 4125 line has gone away, and I have 105% remaining here. Now, 95% of the dose, the cyan colored line, covers the vertebral body, but I still have this large 105%. So I'm going to go ahead and change field 1 to have a 60 wedge, and I'll leave field 2 for the 45 wedge. And we'll see if we can make this dose gradient just a little bit more favorable. Now, because I'm using a different wedge, it's going to have a different attenuation factor. So you see what happened is that my beam weighting needs to change, because I'm letting more transmission for an equally weighted beam. I'm letting more transmission through the 45 wedge, which gives me this 105% hotspot over here. So I'm going to slightly weight my 60 wedge just a little bit more to equal out these hot spots. So now you can see my wedges, my posterior wedge pair. I've decreased my dose gradient. I have a 45 wedge from the posterior right and a 60 wedge from the right posterior and a 45 wedge from the left posterior. Now, I am going to calculate the monitor units. So in this, I need to know what my relative weighting for my calc point is, and then we're going to look up some wedge factors as well. I have an 8x8 field size. 8x8 on this side. Let me recalculate this. 8, 8. We'll make them the same. And we'll just avoid the equivalent square field calculation, and we'll just look everything up for an 8x8 field size. Okay. So if I look field 1, spine CP is getting 100.7. So let's pull some of this information in here. Dose is 100.7. Depth is 8.9. Now I can use my SSD, but my SSD isn't going to be used in the calculation at all. I'm calculating at the ISO center, so 91.1 plus 8.9 is going to give me 100 centimeters. So I'm 100 centimeter SAD. And I have an 8 centimeter equivalent square. So if I look up the monitor units, I have dose divided by S sub C, S sub P, a TMR. My isodose line is going to be 1.0 because I'm at 100. My inverse square factor I need, and then I need a wedge factor. I don't have an off-axis ratio since I'm on the central axis. So 100.7 divided by S sub C. If I pull my 15 MV TMR data tables in, 8x8, I have 0.983, S sub P 0.995. My tissue maximum ratio, if I look at 8 centimeters across the top and I go down to a 9 centimeter depth, I'm at 0.896. Inverse square factor is source to calibration distance, which in my case for 15 MV, source to calibration distance is 102.8. My distance to my point is 100. I square that and I get 1.057. And a wedge factor, I have a 60-degree wedge. 60-degree wedge, 10 by 10, 0.431. .7 divided by 0.983 times 0.995 times 0.896 times 1.057 times 0.431 gives me 252. 252 MU. So the treatment planning system monitor units were 254. So I get a 1% deviation from the two. Now if we look at the other field, field 2, the LPO, my dose is 149.3. Again, I don't have equal weighting on these two fields. I had to change it since I've changed my wedge and I had a little bit more transmission through my 60-degree toe. So I had to preferentially weight the posterior left side, the 45 wedge, a little bit more to get rid of that excess transmission through the 60-degree toe. My depth is 8.4 centimeters. I still have the same equivalent square. My monitor units are still going to be treated the same. The only difference now is my depth component and my wedge factor are going to change. My dose is 149.3. I have the exact same S sub C, the exact same S sub P. If I look at my beam data tables for TMR, I look at 8 centimeters and 8.5 centimeter depth is going to be 0.908. I have the exact same inverse square factor, source to calibration distance divided by source to calculation distance. My calibration distance is 102.8. My distance to my point is 100. I'm at 100 SAD, so my inverse square factor is the same, 1.057. And then my wedge factor is going to be a 45 upper, 10 by 10, 0.516. If I crunch these monitor units, 149.3 divided by 0.983 times 0.995 times 0.908 times 1.057 times 0.516, I get 308.2. The treatment planning system had 309 monitor units. So I get a percent error of less than 0.5%. So it works out pretty well. Now, since we're on the topic of wedges, I want to talk about my wedge factors for these beam data tables. I have 15, 30, 45, and 60 upper, and 15, 30, 45, and 60 lower. So on the Varian machines, we can have an upper wedge set and a lower wedge set. The upper wedge set are primarily what we use all the time. Hardly anybody ever uses a lower wedge set. The lower wedge set mount below the electron tray or photon block adapter that locks into the top of the machine. So we want to focus on the upper wedge set. So this was a posterior wedge pair. Very useful because you have two fields. The therapists only have two fields to treat, two fields to film. It produces a relatively homogeneous dose distribution around your target that you're trying to treat. It spares the anterior portions of the patient's body, such as small bowel, and we don't have to have laterals or posterior or a four-field box to provide a relatively uniform and conformal dose isodose distribution around a target like our vertebral bodies. If I were to change field 2 to a 60-degree right, and then recalculate the dose again, we'll see what happens if we put too much wedge. So now you can see that, let me change the weighting back to equal. So we have a very nice dose distribution. You can see that we're starting to get over wedged just a little bit. We're starting to break up now on the posterior surface and the intersection between these two because I have so much attenuation. I have so much attenuation on the central portion here, the intersection of these two beams caused by both heels of the wedge, that I'm starting to have just a little bit of an over wedging. But the 260-degree wedges probably would be just as nice as the 60 and 45. But I chose 60 and 45 to show you how the dose calculation goes for each of them. Again, this is SAD wedge pair field arrangement.